the ways in which the instruments we use and the strategies we employ to search the sky systematically favor the detection of some objects over others and thereby distort the sample we collect in ways that must be corrected for before any population-level conclusions can be drawn. In the case of interstellar objects, the population to which both Oumuamua and Gennady Borisov belong, this statistical discipline has been particularly active in the years following the discovery of those two objects. As astronomers have worked to estimate from the two confirmed detections how many interstellar objects must be passing through the solar system at any given time, and what that number implies about the rate at which other planetary systems shed material into interstellar space. The calculation, in its broad outlines, begins with the observational facts. Two interstellar objects were detected in the span of roughly 2 years, between October 2017 and August 2019, by surveys with known detection thresholds and known sky coverage rates. From these facts, combined with models of how the detection efficiency of a given survey depends on the size, brightness, and velocity of the objects it is searching for, it is possible to estimate the number density of interstellar objects in the solar neighborhood, that is, how many such objects exist per unit volume of space in the region around our Sun. The estimates that have been published based on the Oumuamua and Borisov detections span a fairly wide range, reflecting the significant uncertainties involved, but they consistently point to a number density that is, in the words of several papers, surprisingly high, much higher than pre-discovery theoretical estimates had suggested, and high enough to imply that interstellar objects are not rare vagrants passing through our solar system once in a geological age, but rather a continuous and significant component of the solar neighborhood's small body population, with perhaps several interstellar objects inside the orbit of Neptune at any given time, and with our solar system experiencing something like one interstellar visitor per year that is large enough and bright enough to be detectable by a sufficiently capable survey. The implications of this high number density are remarkable. If interstellar objects are as common as the Oumuamua and Borisov detections suggest, then the total mass of material being exchanged between planetary systems across the galaxy, carried on the slow currents of interstellar space by ejected comets and asteroids, and whatever other categories of interstellar small body exist, is very large indeed. Estimates of the total mass flux of interstellar cometary material through the solar neighborhood, derived from the inferred number density and the assumed size distribution of the population, suggests that the solar system is being continually bathed in a slow rain of interstellar material, tiny in any individual piece but enormous in aggregate over geological timescales. This material, these fragments of other planetary systems, carrying the chemistry of their origin environments, is not merely passing through. Some small fraction of it must be captured into bound solar system orbits by gravitational interactions with the planets, particularly Jupiter, becoming temporarily or permanently incorporated into the solar system's own small body population. Some fraction may ultimately impact the planets themselves, delivering their chemical cargo to planetary surfaces in the same way that solar system comets are thought to have delivered water and organics to the early Earth. The solar system is not a closed system. It has never been a closed system. It is embedded in a galaxy that is chemically and dynamically connected at every scale, and the interstellar objects passing through it are one of the physical mechanisms through which that connectivity manifests at the local level. The statistical estimates derived from the Oumuamua and Borisov detections also have important implications for the design and capabilities of future sky surveys, because they define the expected rate at which interstellar objects should be detectable by surveys of various depths and sky coverage rates. The Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, or LSST, which began its legacy survey of space and time in the mid-2020s, is expected to be transformative in this context. The Rubin Observatory is designed to survey the entire visible sky repeatedly, with a cadence of roughly 3 days per visit to any given sky position, using an 8.4-meter primary mirror and a 3.2 gigapixel camera to reach faint limiting magnitudes across a wide field of view. By virtually every estimate, this combination of aperture, sky coverage, and cadence makes the Rubin Observatory far more capable than any previous survey for detecting interstellar objects. Estimates suggest that it could detect dozens of interstellar objects per year if the number density inferred from the Oumuamua and Borisov detections is correct, or at minimum several per year, even if the true number density is at the lower end of the estimated range. The prospect of detecting not two but dozens of interstellar objects over the coming decade transforms the study of interstellar visitors from a discipline built on the analysis of individual exceptional discoveries into something approaching a genuine statistical science, one in which population properties can be measured, distributions characterized, and compositional trends identified across a sample large enough to support meaningful generalization. The anticipation surrounding the Rubin Observatory's expected harvest of interstellar objects reflects a broader shift in the way the astronomical community has come to think about these objects in the years since their discovery, a shift from regarding them as exotic anomalies, extraordinary exceptions to the general rule that the solar system's small body population is entirely local in origin, toward regarding them instead as a genuinely important component of the solar neighborhood's dynamic environment, a window into the properties of planetary systems throughout the galaxy that is available in principle to any survey sensitive enough to exploit it. This shift in perspective is itself a significant scientific development because it changes the questions being asked and the data being gathered. Rather than asking simply, what is this specific object made of? The question that dominated the study of both Oumuamua and Borisov, the community is increasingly asking, what is the population of interstellar objects like, in aggregate, and what does the distribution of their properties tell us about the diversity of planetary formation processes across the galaxy? These are questions that can only be answered with a larger sample, and the Rubin Observatory is expected to begin providing that sample in earnest as its survey matures. There is, alongside this forward-looking anticipation, a quieter and more philosophical dimension to the story of interstellar objects that deserves attention, a dimension that concerns not the statistical properties of populations or the design of future surveys, but the simple, profound fact of what it means to hold in your mind the knowledge that comets from other stars are passing through our solar system continuously, that the night sky contains within it, at any given moment, objects that formed around other suns and carry the chemistry of other worlds, objects that are detectable in principle if you look carefully enough and have the right tools. There is something in this knowledge that changes the texture of the night sky, not dramatically, not in a way that announces itself with the same kind of immediacy as a meteor streaking across the field of view or a comet's tail arching across the twilight, but quietly, in the way that all genuinely deep astronomical knowledge changes our relationship to the sky, by adding layers of meaning and connection that were not visible before. The stars have always been other suns. We have known this for centuries, but knowing that their planetary systems shed material that drifts across interstellar space and passes through our own neighborhood is a different and more immediate kind of connection. It is the knowledge that the solar system is not an island but a way station, not a closed garden but an open shore, washed by the slow tides of interstellar material carrying the chemistry of a galaxy that is, in this specific and physical sense, in continuous if gradual communication with itself. The broader context of interstellar object research intersects in interesting and sometimes surprising ways with other areas of active astronomical investigation, including the study of debris disks around other stars, the characterization of protoplanetary disk chemistry through millimeter wave and infrared observations, and the rapidly expanding field of exoplanet atmospheric spectroscopy. Debris disks, the dusty, extended structures seen around many nearby stars that represent the remnants of planetesimal collisions in mature planetary systems, are thought to be the source of much of the interstellar cometary material drifting through the galaxy, with mutual collisions among the cometary population of a system continuously grinding down larger bodies into smaller fragments and releasing material that can then be ejected by planetary gravitational encounters or by the radiation pressure of the host star. The properties of debris, disks, their masses, their spatial extents, their grain-size distributions, their compositions as inferred from the spectral energy distributions of their thermal emission, encode information about the underlying populations of planetesimals that generate them, and this information can be compared against the properties of interstellar objects like 2I Borisov to build a more complete picture of the connection between disk structure and interstellar material output. Systems with more massive or more active debris disks might be expected to eject more material into interstellar space, contributing more interstellar comets to the galactic population, and observations of the correlation between debris disk properties and stellar age, spectral type, and multiplicity are beginning to provide the observational constraints needed to test this expectation. The chemistry of protoplanetary disks, studied through the millimeter wave and submillimeter wave emission lines of molecular species in the gas phase of the disk, accessible to observatories like ALMA with extraordinary sensitivity and spatial resolution, also connects directly to the question of interstellar comet composition. The molecules detected in protoplanetary disks around nearby young stars include many of the same species found in cometary Comet water: carbon monoxide, carbon dioxide, formaldehyde, methanol, and increasingly complex organics, and the spatial distributions and abundance ratios of these molecules within the disk encode information about the temperature structure of the disk, the location of various ice lines, and the degree of chemical processing that has occurred as material moves inward from the cold outer disk toward the warmer inner regions where planets ultimately form. By comparing the molecular abundances measured in protoplanetary disks against the molecular abundances measured in comets, both solar system comets and interstellar visitors like Borisov, astronomers can trace the chemical inheritance that connects disk chemistry to cometary chemistry, mapping the pathway by which the molecules assembled in the cold outer disk are eventually incorporated into the icy bodies that become comets and, ultimately, potential interstellar travelers. This connection between the chemistry of planet-forming disks observed around other stars and the chemistry of comets observed in our own solar system and passing through it from elsewhere is one of the most exciting frontiers in contemporary planetary science, a frontier where the tools of radio astronomy, infrared spectroscopy, and solar system science converge on questions about the universality of the chemistry that undergirds planets and, perhaps, life. The James Webb Space Telescope, which began scientific operations in 2022, has opened new possibilities in this area that are only beginning to be realized. With its extraordinary sensitivity in the near-infrared and mid-infrared wavelength ranges where many key molecular species emit or absorb strongly, and where the thermal emission of warm dust in protoplanetary disks, cometary Comet, is accessible with unprecedented detail. The JWST is expected to transform the study of both protoplanetary disk chemistry and cometary composition in ways that will directly inform the interpretation of future interstellar object detections. Already, JWST observations of protoplanetary disks have revealed chemical complexity that previous instruments could only hint at, detecting molecular species in disk atmospheres that had never previously been accessible to observation, and building a picture of disk chemistry that is richer and more varied than earlier models had suggested. When the next interstellar comet arrives, as it surely will, perhaps within years, if the Rubin Observatory's expected detection rate proves accurate, it will be studied in a scientific context transformed by JWST's contributions to our understanding of disk chemistry, cometary composition, and the molecular inventory of the universe. And the portrait that emerges of that future visitor will be correspondingly richer, more detailed, and more deeply connected to the broader narrative of cosmic chemical evolution that 2I Borisov helped to introduce into the mainstream of planetary science. There is a particular quality of patience that the universe demands of those who study it seriously, not the passive patience of waiting for something to happen, but the active, engaged patience of continuing to think carefully about something long after the immediate excitement of its discovery has faded, long after the press releases have been written, and the conference presentations given, and the initial papers published. In the quieter and often more productive period, when the data sits with you and you sit with the data and the questions it raises, begin to deepen and ramify in ways that the initial burst of activity did not allow for. This kind of patient, sustained engagement with a difficult problem is what distinguishes the deepest scientific work from the merely competent, and it is what the study of 2I, Borisov, has increasingly demanded and received in the years since its passage through the solar system, years during which astronomers have returned repeatedly to the data, refined the analyses, challenged the initial interpretations, and in some cases arrived at conclusions that complicate or nuance the picture that emerged in the immediate aftermath of the discovery. Science is not a process that produces final answers. It is a process that produces progressively better questions. And the study of 2I, Borisov, has been generous in this regard. Generous in the questions it has prompted, generous in the directions it has opened, generous in the ways it has connected the specific puzzle of a single interstellar comet to the much broader and deeper puzzle of how planetary systems form and evolve and shed material throughout the galaxy over timescales that dwarf the entirety of human civilization. One of the directions in which the study of 2I, Borisov, has extended most productively is the comparison between Borisov and the population of solar system comets classified as dynamically new comets, making their first or one of their first passages through the inner solar system after spending billions of years in the Oort Cloud, where they have been preserved at temperatures close to absolute zero, shielded from the thermal and photolytic processing that comets in shorter period orbits experience repeatedly over their observational histories. Dynamically new comets are of particular scientific interest because they are thought to be among the most pristine cometary bodies accessible to observation, least processed by repeated solar heating, most representative of the original chemical composition of the outer protoplanetary disk from which they formed, most likely to retain the highly volatile species like CO, CO2, and various complex organics that are depleted by thermal processing over time. They are also, interestingly, known to exhibit certain behavioral characteristics that distinguish them from their more processed counterparts. They tend to show elevated activity at large heliocentric distances, driven by the sublimation of hypervolatile species before the comet has warmed sufficiently to drive significant water sublimation, and they can display outbursts and structural changes as their previously unexposed surfaces encounter solar radiation for what may be effectively the first time. The parallels with 2I, Borisov, which had presumably spent its entire post-ejection history in the cold interstellar medium, never approaching any star closely enough to experience significant thermal processing, and which showed elevated CO production and hints of fragmentation consistent with the behavior of a thermally pristine body encountering stellar warmth for the first time, are striking, and the comparison has proven to be one of the most scientifically productive frameworks for interpreting Borisov's observed properties. The comparison is not perfect. Of course, science's comparisons rarely are, because dynamically new solar system comets, while pristine in the sense of being unprocessed by solar heating, have not been entirely isolated from energetic processing during their billions of years in the Oort Cloud. Cosmic rays, the high-energy charged particles that pervade the interstellar medium and penetrate even into the outer reaches of the solar system, continuously irradiate the surfaces of Oort Cloud comets, processing the uppermost layers of their surfaces over geological timescales, breaking molecular bonds, driving chemical reactions, and ultimately converting the original volatile-rich ices near the surface into a refractory, organic-rich crust that is depleted in the most volatile species. This cosmic ray processing affects roughly the top few meters of a cometary nucleus over the age of the solar system, leaving the deep interior largely unaffected, but fundamentally altering the surface composition in ways that influence the comet's behavior when it first approaches the Sun. An Oort Cloud comet making its first perihelion passage must shed this processed surface layer before the pristine material beneath is exposed, and this shedding process, driven by outgassing of the volatiles trapped beneath the irradiated crust, accounts for much of the elevated, sometimes erratic activity seen in dynamically new comets at large, heliocentric distances. For 2I, Borisov, the equivalent of this cosmic ray processing would have occurred over the entire duration of its interstellar journey, whatever that duration was, potentially billions of years, during which the comet's surface would have been continuously irradiated by the ambient cosmic ray flux of the interstellar medium, which is comparable in intensity to, and in some energy ranges higher than, the cosmic ray flux in the outer solar system. The surface of 2I, Borisov, at the moment of its arrival in the solar system, would therefore have been a product of billions of years of cosmic ray, processing a dark, organic-rich, refractory crust overlying the pristine, volatile-rich interior, conceptually similar to the processed surfaces of Oort Cloud comets, but potentially more extensively modified given the longer irradiation timescale. The detection of CO in large quantities in Borisov's coma is interesting in this context because CO is among the most volatile of cometary species and among the most susceptible to depletion by thermal and cosmic ray processing. The fact that Borisov released CO abundantly suggests either that its interior was very rich in CO ice, as might be expected for a comet that formed in the cold outer regions of its home system, or that the cosmic ray processing of its surface had not fully depleted the CO in the layers being actively sublimated during its perihelion passage, or some combination of both effects. Distinguishing between these possibilities from remote observations alone is not straightforward, and the uncertainty reflects a broader limitation of remote cometary science, the inability to directly sample the interior composition of a nucleus without a spacecraft capable of drilling or sampling below the surface. The Rosetta mission's Philae lander touched down on Comet 67P and conducted in situ measurements. But even Philae's data was limited to the very surface and near surface of the nucleus, and the extent to which that surface composition represents the bulk interior composition of the comet remains a subject of active debate. For an interstellar comet accessible only to remote observation, the uncertainty is correspondingly greater. We measure what comes out of the nucleus, and we infer from that what must be inside, but the inference is model dependent, and the models themselves carry significant uncertainties. This fundamental limitation of remote observation, the gap between what we measure at the surface and what we infer about the interior, is one of the primary motivations for proposals that have circulated within the planetary science community for spacecraft missions capable of intercepting and studying interstellar objects in situ. The concept of such a mission is not new. Even before Oumuamua was discovered, theorists and mission designers had considered the possibility that an interstellar object might be detected with sufficient advance notice to permit a spacecraft intercept, and had outlined the technical requirements for such a mission: the launch vehicle performance, the propulsion technology, the trajectory design, the instrument complement, in enough detail to demonstrate that, while challenging, such a mission was not necessarily beyond the reach of near-term space technology, particularly if the object was discovered early enough after entering the solar system to allow a trajectory to be designed and a launch to be executed before the window closed. The discovery of Oumuamua demonstrated that interstellar objects would not always provide such advance notice. Oumuamua was found after its closest approach, far too late for any credible intercept mission. But the discovery of 2I, Borisov, found weeks before perihelion, demonstrated that with the right survey capabilities, specifically the kind of deep, wide-field, high-cadence survey that the Rubin Observatory is designed to conduct interstellar objects, could in principle be found early enough to make an intercept mission at least theoretically possible. The European Space Agency's Comet Interceptor mission, approved in 2019 and targeting a launch in the late 2020s, is designed precisely for this possibility. Comet Interceptor is a fast response mission concept in which the spacecraft will be launched to a gravitationally stable point in space, the Sun-Earth L2 point, where the James Webb Space Telescope also resides, and wait there in a kind of cosmic readiness for the discovery of a suitable target, either a dynamically new solar system comet making its first inner solar system passage, or, if the astronomical fortune proves sufficiently generous, an interstellar object detected with enough advance notice to permit a trajectory to be planned and executed. The mission architecture involves a main spacecraft and two smaller subprobes, the ensemble designed to fly through the target comet's coma at high speed, making rapid in situ measurements of the gas composition, dust properties, and plasma environment, while also imaging the nucleus at resolutions far beyond anything achievable from Earth or from near-Earth orbit. If Comet Interceptor encounters an interstellar object, the scientific return would be extraordinary for the first time. The in-situ chemical measurements that have been made at solar system comets like Halley, Churyumov-Gerasimenko, and Wild 2 would be applied to a comet from another star, providing direct, unambiguous measurements of the volatile composition, the isotopic ratios, and the physical structure of a body that formed in an entirely different planetary system and has spent billions of years in the interstellar medium. The prospect of such a measurement of actually flying through the coma of an interstellar comet, tasting its chemistry directly with mass spectrometers, rather than inferring it remotely from spectral lines, represents perhaps the most ambitious and scientifically transformative goal in the emerging field of interstellar object science. It would resolve, in principle, many of the uncertainties that remote observation leaves unaddressed. The question of whether the bulk composition of an interstellar comet truly resembles that of solar system comets as closely as the remote observations of Borisov suggest. The question of what isotopic ratios are preserved in the ice of an interstellar comet and what those ratios imply about the elemental abundances of its home system, the question of what complex organic molecules are present in the coma, and at what abundances relative to the simpler species that are more readily detected from Earth. These are questions about the deepest level of chemical similarity between our solar system and others, questions that go beyond the broad molecular categories detectable from Earth and reach into the specific molecular structures and isotopic signatures that encode the most precise information about formation conditions and chemical history. To answer them from in situ measurements at an interstellar comet would be to take a chemical sample, however indirect and fleeting, from another planetary system to reach across the interstellar void, not with a radio signal or a reflected photon, but with an instrument package traveling at tens of kilometers per second through the outgassed remnants of ice that formed around another star. It is perhaps the most audacious scientific goal currently within the realm of the conceivable, and the fact that it is being seriously planned and funded and designed rather than merely dreamed about reflects how profoundly the discovery of Oumuamua and 2I Borisov has transformed the landscape of what the planetary science community believes is worth attempting. Beyond the spacecraft mission concepts, the study of interstellar objects has also stimulated renewed interest in the theoretical modeling of planetary system formation and evolution, specifically in the dynamics of how small bodies are ejected from forming planetary systems and what determines the rate of ejection, the size distribution of ejected bodies, and the chemical composition of the ejected population. These theoretical questions connect directly to fundamental issues in planet formation theory that remain incompletely resolved even for our own solar system. Questions about the initial mass function of planetesimals, the efficiency of giant planet formation, and the timescale of giant planet migration, the role of stellar flybys and galactic tidal forces in sculpting the outer regions of planetary systems, and the long-term dynamical stability of small body populations over the multi-billion-year lifetimes of mature planetary systems. Each of these theoretical uncertainties translates into an uncertainty in the predicted properties of the interstellar object population, and conversely, each observational measurement of an interstellar object's properties, its size, its composition, its velocity relative to the local standard of rest, its activity level, its structural properties, provides a constraint on the theoretical models that can be used to refine them. The two confirmed interstellar objects have already begun this process of theoretical refinement, and the much larger sample expected from the Rubin Observatory's legacy survey of space and time will carry it very much further, building toward a genuinely data-driven understanding of planetary system formation processes that is grounded not in the study of a single system, our own, but in the study of the aggregate output of many systems distributed throughout the galaxy, sampled through the slow, patient medium of the interstellar comets they have shed into the dark between the stars. There is a sense in which every scientific discovery exists in two registers simultaneously: the register of the specific, immediate, technical finding, which speaks to specialists in the language of measurements and error bars and model fits and statistical significance, and the register of the broader meaning, which speaks to something deeper and more universal in the human relationship to knowledge, to the cosmos, to the question of what we are, and where we come from, and whether we are alone in our curiosity about these things. Most scientific discoveries live primarily in the first register and touch the second only tangentially. If at all, they extend the map of the known by a small increment in a direction that matters to those who already understand the map well enough to know what was missing from it without fundamentally altering the character of the map itself or the relationship of the map maker to the territory it represents. But occasionally a discovery arrives that operates in both registers with equal force, that is technically significant and humanly significant in ways that reinforce each other, that expands the map, and also changes what it means to make the map, that answers specific questions, while simultaneously opening a view onto something so large and so deep that the specific questions it answers seem almost incidental to the vista it reveals. The discovery of 2I, Borisov, and the subsequent discovery of what it was made of is one of these rarer events, a finding that is scientifically important in the technical sense, and also quietly profound in a way that is difficult to articulate without risk of overstatement, but that is equally difficult to honestly ignore. The profundity, if that is the right word, lies in the familiarity. It lies in the fact that a comet formed around another star, in conditions that we cannot directly observe, and in a system that we cannot visit, carries within it the same molecular building blocks, water, carbon monoxide, carbon-bearing radicals, silicate dust, that we find in the comets of our own solar system. This familiarity could be interpreted in a modest way as simply confirming that the same physical and chemical processes that operate in our solar system's protoplanetary disk also operate in other disks around other stars. A confirmation of the universality of physics that, while gratifying, is perhaps not deeply surprising, given how well established the laws of physics are and how little reason we have to think they would be different elsewhere. But the familiarity can also be interpreted in a more expansive way, as evidence for a genuine chemical coherence across the galaxy, as a suggestion that the specific molecular inventory of planet-forming regions, the particular mixture of ices and organics and silicates that gets incorporated into comets and then delivered to forming planets, is not merely governed by universal physics in the abstract, but is actually quite similar in its concrete molecular detail from system to system, at least among systems of broadly similar stellar type and galactic environment. And this more expansive interpretation, if it is correct, carries implications for the question of life that are almost too large to fully think through in a single sitting, because it suggests that the chemical prerequisites for life, if those prerequisites are indeed the kinds of molecules found in comets, are not a local accident but a galactic regularity, scattered throughout the Milky Way on the slow currents of interstellar cometary traffic, available in principle to any planet that happens to be in the right place at the right time to receive them. To think carefully about this implication is to encounter one of the deepest unresolved tensions in astrobiology, the tension between the universality of chemistry and the contingency of biology. Chemistry, as 2I, Borisov reminds us, is universal in the sense that the same atoms and molecules appear wherever the conditions for their formation are met, and those conditions are themselves widely distributed throughout the galaxy. The molecular building blocks of life, amino acids, nucleobases, sugars, lipids, can be synthesized abiotically from simpler precursors under conditions that are common in interstellar clouds, in protoplanetary disks, in cometary Comet, and on the surfaces of rocky planets receiving energy from their stars. This universality of abiotic organic chemistry is one of the most robust findings of astrobiology, supported by laboratory experiments, by observations of interstellar and cometary chemistry, and by the analysis of carbonaceous meteorites that have delivered complex organic molecules to Earth's surface for billions of years, including the famous Murchison meteorite, which fell in Australia in 1969 and has been found to contain more than 90 amino acids, only 20 of which are used by life on Earth. The universe is extraordinarily good at making the raw materials of life. It makes them everywhere, apparently from the same basic toolkit of atoms and reactions that it deploys throughout the cosmos without preference or discrimination. Biology, however, is not merely chemistry. The transition from a mixture of organic molecules to a self-replicating, metabolically active, evolving system. The transition that we call the origin of life is something that we do not yet understand at the level of mechanism, despite decades of brilliant experimental and theoretical work. We know that this transition happened at least once, on Earth, sometime in the first few 100 million years after the planet's surface cooled enough to support liquid water, because we are here, reading and writing and thinking, which is itself the most direct possible evidence that the origin of life is not an impossible event. But knowing that it happened once tells us very little about how often it happens in general, because we cannot determine from a single example whether the origin of life is a highly probable event that occurs whenever conditions are suitable, a robust, almost inevitable outcome of the chemistry that the universe provides, or a highly improbable event that occurred on Earth by a remarkable concatenation of fortunate circumstances and might not occur again in exactly the same form anywhere else in the universe in the observable future. This is the central uncertainty of astrobiology, and it is one that no amount of cometary chemistry, however rich and however familiar, can resolve by itself. 2i. Borisov tells us that the raw materials are universal. It does not tell us what the universe does with the raw materials. And yet even this limited telling, even the confirmation that the chemistry of comets is broadly similar from system to system, that the molecular prerequisites for prebiotic chemistry are distributed throughout the galaxy and not confined to our solar neighborhood, is more than we knew before, and it tilts the probabilistic landscape of the astrobiology question in a direction that most researchers in the field find at least modestly encouraging. If the chemical prerequisites are universal, then the question of life's frequency in the universe reduces more cleanly to the question of how often the transition from chemistry to biology occurs given suitable conditions. And this, while still deeply uncertain, is at least a cleaner and more tractable question than it would be if the chemical prerequisites were themselves rare and contingently distributed. The universality of cometary chemistry, as evidenced by 2i. Borisov, removes one layer of contingency from the origin of life problem. It suggests that the universe is not stingy with the raw materials of biology, but is in fact extraordinarily generous with them, distributing them widely and continuously through the mechanism of interstellar cometary delivery, among other processes. And this is a finding of genuine significance for how we think about the prevalence and distribution of life. The cosmos, even if it cannot by itself resolve the deeper question of how often chemistry becomes biology. There is another dimension of 2i, Borisov's significance, that has received less attention in the scientific literature, but that is worth dwelling on here. In the context of this longer and more reflective narrative, the dimension of timing. 2i, Borisov, was discovered in August 2019, roughly 2 years after the discovery of Oumuamua. Both objects were discovered because human beings had built, by that point in history, telescopes and digital detectors and computational tools, sophisticated enough to find them tools that did not exist 30 years earlier, and that were themselves the products of a specific and contingent technological development trajectory that might easily have proceeded differently and produced a different set of capabilities at a different time. The fact that Oumuamua was discovered in 2017 and not in 1987 or 2047 is not a cosmic coincidence, but a historical contingency. It reflects where humanity happened to be in its technological development at that particular moment, which reflects in turn the specific sequence of scientific investments, engineering achievements, and institutional decisions that led to the Pan-STAR survey being operational with the sensitivity it had at that time. And the fact that 2i, Borisov, was discovered in 2019 with enough advance notice to permit detailed scientific study reflects the specific capabilities of Gennady Borisov's home-built telescope and his personal practice of systematic sky scanning, combined with the rapid global response of a community that had been primed by the experience of Oumuamua to recognize and respond to interstellar objects with the urgency they deserve. This contingency of timing, the fact that the discovery of interstellar objects required a specific level of technological capability that humanity reached at a specific historical moment, is itself a scientifically interesting datum, in the same way that any observation of what was and was not detectable with the instruments of a given era is scientifically interesting. Before pan-stars and the generation of wide-field digital sky surveys it represents, interstellar objects almost certainly passed through the solar system, undetected, passing through our neighborhood in the darkness, revealing themselves to no instrument, leaving no trace in any archive, departing again into the interstellar medium without any record of their passage. They were there in the same numbers that they are now, but they were invisible to us because we had not yet built the eyes capable of seeing them. The history of astronomy is in large part the history of building better eyes, telescopes of greater aperture and sensitivity, detectors of greater efficiency and dynamic range, surveys of greater sky coverage and temporal cadence, and each increment of improved capability reveals a universe that was always there, but previously beyond reach, adding new categories of object and phenomenon to the map of the known. The discovery of interstellar objects is the most recent example of this pattern, and it serves as a reminder that the map of the known is always and necessarily incomplete, that there are categories of object and phenomenon that exist in the universe right now, passing through our solar system, or orbiting in our galaxy, or shaping the evolution of our cosmos, that we have not yet detected because we have not yet built the instruments capable of detecting them, and that each new generation of astronomical capability will reveal some of them to us, expanding the map in directions we may not yet be able to anticipate. The Rubin Observatory represents the next major increment of this capability, at least in the domain of solar system and interstellar object science, and the community's anticipation of its expected harvest of new discoveries, including, almost certainly, many more interstellar objects than the two currently known, reflects a hard-won understanding of how transformative improvements in observational capability can be. But even before the Rubin Observatory's full survey potential is realized, the field of interstellar object science has been permanently changed by the discoveries of Oumuamua and Borisov, changed in the specific sense that a field that previously had no confirmed examples of its primary subject of study now has two, and with two examples comes the beginning of what might eventually become a comparative science, the ability to compare properties across a sample, to identify what is common and what varies, to ask whether the differences between Oumuamua and Borisov reflect genuine diversity in the interstellar object population, or simply the contingent circumstances of how and when each was observed. Oumuamua and Borisov are strikingly different from each other, one showing no cometary activity at all and exhibiting anomalous non-gravitational acceleration, the other behaving in every observable respect like a perfectly ordinary comet. And this difference between the first two confirmed interstellar objects raises immediately the question of how diverse the interstellar object population truly is, whether it contains multiple distinct categories of objects with different compositions and dynamical histories, and what those categories can tell us about the diversity of the planetary systems that produce them. These are questions that two objects cannot answer, but that a larger sample, the sample that the Rubin Observatory and future instruments will provide, can begin to address in a scientifically meaningful way, building toward an understanding of interstellar objects, not as individual curiosities, but as a population with measurable statistical properties, encoding the aggregate history of planetary formation throughout the galaxy. The contrast between Oumuamua and Borisov is so sharp, in fact, that it has become one of the central puzzles of the field, a puzzle that has generated an enormous amount of theoretical work aimed at explaining how two objects from the same broad category of interstellar visitors could differ so dramatically in their observed properties. Oumuamua had no detectable coma, no detectable outgassing of any identified molecular species, and an anomalous non-gravitational acceleration that remains unexplained to the satisfaction of the entire community, despite years of theoretical effort. Borisov had a well-developed coma, robust outgassing of multiple molecular species including water and carbon monoxide, and a trajectory that was entirely consistent with pure gravitational dynamics. No non-gravitational acceleration of any kind was detected or required to explain its orbital evolution. If both objects are interstellar comets, fragments of icy bodies ejected from planetary systems around other stars, then their dramatic differences in behavior must reflect real differences in their physical properties, their compositions, their thermal histories, or some combination of all three. The most widely discussed explanation for Oumuamua's lack of cometary activity is that it was not an icy body in the same sense that Borisov was, that it had a different composition, perhaps dominated by more refractory materials, or by exotic ices like molecular hydrogen or nitrogen that would sublimate without producing the standard molecular signatures of a water ice or CO ice comet, or that its surface had been so thoroughly processed by cosmic ray irradiation during its long interstellar journey that all near-surface volatiles had been destroyed, leaving only a refractory organic crust incapable of producing a visible coma even as it approached the sun. None of these explanations is fully satisfactory to all researchers in the field, and the mystery of Oumuamua's anomalous acceleration in particular remains genuinely open, a reminder that the universe is under no obligation to present us with objects that are easy to understand, and that the most interesting discoveries are often the ones that resist the first several attempts at explanation and demand instead a more fundamental rethinking of the categories and assumptions with which we approach the problem. There is something that happens to a scientific field when it transitions from 0 confirmed examples of its central subject to 2, a transition that sounds modest when described in those terms, but that is, in practice, one of the most intellectually consequential shifts that can occur in an empirical discipline. Before the first confirmed example, the field operates in a mode that is necessarily speculative and theoretical, building models and making predictions in the absence of the observational anchor that would allow those models to be tested and refined against reality. With the first confirmed example, the field gains that anchor, but only one and a single example, however carefully studied, cannot distinguish between what is universal and what is idiosyncratic, between what is typical of the class and what is a peculiarity of the individual. With 2 confirmed examples, the field gains something qualitatively different from what the first example provided, not just twice as much data, but the beginning of comparison, the first tentative glimpse of what varies and what stays the same, the first empirical constraint on the diversity of the population rather than just its existence. And with that glimpse of diversity comes the first real possibility of a comparative science of asking not just what is this object, but how do objects of this type differ from one another? And what do those differences tell us about the processes that created them and the environments they came from? The comparison between Oumuamua and 2I, Borisov, has been, in this sense, one of the most intellectually productive exercises in recent planetary science. Not because it has produced definitive answers to the questions it raises, but because the sharpness of the contrast between the 2 objects has forced the community to confront the full range of possibilities for what interstellar objects can be, and in doing so, has pushed theoretical models of interstellar object formation and evolution to their limits in ways that may ultimately require genuinely new frameworks to accommodate. The contrast is, as noted in the preceding part of this narrative, dramatic. Where Borisov was familiar, a comet behaving like a comet, outgassing like a comet, looking like a comet in every measurable respect, Oumuamua was strange in almost every dimension of its observed behavior, refusing to fit cleanly into any existing category of solar system, small body, and generating a proliferation of theoretical explanations that reflects the depth of the community's uncertainty about its nature. The explanations proposed for Oumuamua's anomalous behavior have ranged from the physically conventional to the genuinely exotic, and the fact that no single explanation has achieved consensus acceptance more than half a decade after the object's discovery is itself a significant scientific datum, a measure of how far outside the range of normal cometary behavior Oumuamua's properties lie, and of how fundamentally it challenges our understanding of what interstellar objects are and how they come to be. Among the explanations proposed for Oumuamua's non-gravitational acceleration, the property that is proven most resistant to conventional explanation, the most widely discussed within the mainstream scientific community, involved the outgassing of a highly volatile species that was present in the object in large quantities, but that produced no detectable spectroscopic signature, either because it was intrinsically difficult to detect at the wavelengths accessible to the instruments used to observe Oumuamua, or because the outgassing was occurring at a rate too low to produce detectable emission against the sky background, but still sufficient to provide the observed acceleration. Molecular hydrogen has been proposed as one candidate, with several groups arguing that an object rich in solid molecular hydrogen, sometimes called a hydrogen iceberg, could outgas silently, producing no detectable coma or spectral features, while still providing enough mass flux to account for the observed acceleration through rocket-like momentum transfer. The problem with this explanation is that molecular hydrogen ice is extremely difficult to form and preserve under astrophysical conditions. It requires temperatures close to absolute zero and is rapidly destroyed by cosmic ray irradiation, which would process the outermost layers of any hydrogen iceberg beyond recognition over the timescales required for interstellar travel. The proposal by Stephen Desch and Alan Jackson that Oumuamua might be a fragment of nitrogen ice shed from the surface of a Pluto-like body in another planetary system addresses some of these difficulties but raises others, including the question of whether the mechanism for producing and ejecting such fragments is physically plausible, and whether the inferred size and shape of Oumuamua are consistent with the expected properties of such a fragment. The more exotic end of the explanatory spectrum for Oumuamua includes the proposal by Avi Loeb and Shmuel Bialy that the object might be a thin sheet of artificial material, a light sail. In the language of the emerging field of directed energy propulsion pushed by solar radiation pressure, in a way that would naturally produce the observed non-gravitational acceleration without requiring any outgassing at all. This proposal, which Loeb has continued to advocate and expand upon in his subsequent writing and public engagement, attracted enormous attention and generated considerable controversy, with the majority of the planetary science community expressing skepticism on the grounds that the evidence for an artificial origin is far weaker than the evidence for natural explanations that, while individually imperfect, collectively span a plausible range of possibilities consistent with known astrophysics. The debate over Oumuamua's nature, conducted largely in the scientific literature, but also in the pages of popular science publications and in public forums of various kinds, has been one of the more unusual episodes in recent astronomical history, a genuine scientific controversy, complete with competing hypotheses and contested evidence, conducted partly in the normal, quiet channels of peer review and partly in the more turbulent waters of public scientific discourse, with the usual attendant difficulties of signal and noise, of genuine scientific argument and rhetorical performance, of the productive uncertainty of real science, and the occasionally less productive certainty of scientific celebrity. The debate has not been resolved, and it may not be resolved without additional data, specifically without additional interstellar objects that can be studied in sufficient detail to determine whether Oumuamua's properties fall within the natural range of variation of the interstellar object population, or represent something genuinely anomalous within that population. This is where the connection between Oumuamua and Borisov and the future of interstellar object science becomes most immediate and most consequential, because the fundamental question of whether Oumuamua was a natural object behaving strangely or something entirely outside the category of natural solar system analogs can only be resolved by expanding the sample, by finding and characterizing enough interstellar objects to build a genuine statistical picture of what the population looks like, what its normal range of properties is, and whether Oumuamua falls within that range or outside it. With two confirmed interstellar objects, one of which is perfectly ordinary and one of which is deeply mysterious, the sample is too small to say anything definitive about population statistics. With 10 or 20 or 50 interstellar objects, the picture would be very different. Patterns would emerge, categories would suggest themselves, the range of normal behavior would become empirically defined rather than theoretically assumed, and the question of where Oumuamua sits relative to that range could be addressed with the kind of statistical rigor that the current two-object sample cannot support. The Rubin Observatory's expected harvest of interstellar objects is therefore not merely a quantitative improvement on the existing situation, but a qualitative transformation. The transition from a discipline that reasons primarily from theory and individual examples to one that can reason from population statistics with all the additional power and testability that population-level reasoning provides. The theoretical work stimulated by the Oumuamua Borisov comparison has also produced significant advances in our understanding of the processes by which different types of objects might be ejected from planetary systems and of the expected compositional diversity of the interstellar object population, given the diversity of planetary systems known to exist throughout the galaxy. The exoplanet revolution of the past 3 decades, the discovery, through radial velocity surveys, transit photometry, direct imaging, and other techniques, of thousands of planets orbiting stars throughout the Milky Way, has revealed a breathtaking diversity of planetary system architectures. From tightly packed systems of small rocky planets orbiting close to their stars, to systems dominated by gas giants at a variety of orbital distances, to systems with planets on highly eccentric orbits that sweep through wide ranges of heliocentric distance over the course of a single orbit, to systems apparently lacking any Jupiter analog and dominated instead by super-Earths and mini-Neptunes in configurations that have no direct parallel in our own solar system. This diversity of planetary architectures implies a corresponding diversity in the dynamical histories of those systems and in the properties of the small body populations they harbor, and eject a diversity that should be reflected in the properties of the interstellar objects those systems contribute to the galactic pool, and that should, in principle, be readable from careful statistical analysis of the interstellar object population if the sample is large enough to support such analysis. The implications of this theoretical picture are striking. If planetary systems with different architectures, different numbers and masses of giant planets, different orbital configurations, different levels of dynamical excitation in their small body populations eject interstellar objects with systematically different properties, then the statistical distribution of interstellar object properties in the solar neighborhood should encode information about the distribution of planetary system architectures in our galactic neighborhood, weighted by the ejection efficiency and interstellar survival time of objects from different system types. This is a form of galactic archaeology, reading the properties of the local interstellar object population to reconstruct the history of planetary formation in the surrounding stellar neighborhood that is conceptually analogous to other forms of archaeological reasoning in astronomy, such as reading the chemical abundances of old stars to reconstruct the nucleosynthetic history of the galaxy, or reading the structure of the cosmic microwave background to reconstruct the conditions of the early universe. It is a way of using what is locally accessible, the interstellar objects passing through our solar system, to learn something about what is globally true, the diversity and history of planetary systems throughout galaxy, in the same way that a geologist reads the rock record of a single outcrop to learn something about the broader geological history of a region. The analogy is not perfect, and the practical challenges of extracting this kind of galactic population information from the interstellar object sample are formidable, but the conceptual framework is sound, and the prospect of building it into a genuinely quantitative science over the coming decades of Rubin Observatory operations is one that excites many researchers in the field deeply and quietly, in the way that the best scientific prospects always excite, not with the loud excitement of a completed discovery, but with the softer, more sustained excitement of a direction clearly worth pursuing, a path whose destination cannot yet be seen, but whose first steps are visible and inviting. The role of stellar environments in shaping the interstellar object population is another dimension of the theoretical picture that deserves attention here, because it connects the study of interstellar objects to the broader question of how the galactic environment, the density of stars, the frequency of stellar encounters, The structure of the galactic disk and its spiral arms influences the evolution of planetary systems over geological timescales. Stars in the Milky Way do not exist in isolation. They move through the galaxy on complex orbits that carry them through regions of varying stellar density, occasionally bringing them close enough to other stars for gravitational interactions to be significant, close enough, in some cases, to perturb the outer regions of each other's planetary systems, nudging cometary populations into new orbits, stripping material from the outermost reaches of protoplanetary disks, or even exchanging small bodies between systems in the most extreme close encounters. The frequency of such stellar encounters depends on the local stellar density and on the relative velocities of the encountering stars, and it varies significantly across different regions of the galaxy. Encounters are more frequent in the dense central regions of the Milky Way and in star clusters where stellar densities are orders of magnitude higher than in the local solar neighborhood, and less frequent in the sparse outer regions of the galactic disk. The rate at which interstellar objects are produced and distributed throughout the galaxy is therefore not uniform, but reflects the spatial and temporal structure of the galaxy's stellar population, with denser and more dynamically active regions contributing more interstellar objects per unit volume and per unit time than more quiescent regions like our own local neighborhood. This connection between galactic structure and interstellar object production has an interesting implication for the interpretation of the number density of interstellar objects inferred from the Oumuamua and Borisov detections. If the solar system is currently passing through a region of average stellar density and average dynamical activity, then the inferred number density represents the average galactic interstellar object density in the solar neighborhood, integrated over the timescale during which objects produced in various environments have had time to diffuse through the galaxy and reach our region of space. But if the solar system has recently passed through a region of higher stellar density, such as a spiral arm, where star formation is more active and stellar encounters more frequent, then the local number density of interstellar objects might be temporarily elevated above the long-term average, reflecting a recent burst of production that has not yet had time to diffuse more broadly through the galactic disk. Disentangling these possibilities requires understanding both the solar system's galactic orbit over the past few billion years and the relationship between stellar environment and interstellar object production efficiency, relationship that is still being worked out theoretically, and that will require the kind of large interstellar object sample that the Rubin Observatory promises to provide before it can be tested observationally. The universe, as always, offers its deepest secrets only to those who are willing to gather enough data and to wait long enough, and to think carefully enough about what the data means when it finally arrives. There is a particular kind of ending that is not really an ending at all, a conclusion that arrives not because the story has finished, but because the story has grown large enough and deep enough and sufficiently entangled with other stories that the narrative thread must eventually be gathered back toward itself and held up for a moment of reflection before it continues onward into the future in ways that no single telling can fully anticipate or contain. The story of 2I, Borisov, is such an ending, not a conclusion in the scientific sense, because the science continues and will continue for decades, but a pause point, a place where it is possible to step back from the accumulation of detail and measurement and theoretical interpretation and look at the whole picture from a sufficient distance to see what it actually says about the universe and about our place within it, and about the extraordinary and still unfolding enterprise of trying to understand, with finite instruments and finite minds and finite time, something that is infinite in its extent and incomprehensibly rich in its complexity. To stand at this pause point and look back at everything this small, cold, ancient traveler revealed during its brief passage through our solar system is to feel something that is difficult to name precisely, but that is recognizable to anyone who has spent time thinking seriously about astronomy. Combination of genuine scientific satisfaction and quiet, abiding wonder, the sense of having learned something real and important about the universe, while simultaneously having had the size and strangeness of the universe made more vivid and more present to the imagination than it was before. What 2I, Borisov revealed, In the most essential and compressed summary is this: the universe makes comets the same way everywhere, or at least it makes them similarly enough that a comet formed around another star, traveling through the interstellar medium for perhaps billions of years, arriving in our solar system as the most exotic visitor in the history of recorded astronomy, is recognizable chemically, physically, behaviorally, recognizable as a comet. This recognition is not trivial. It is, in fact, one of the most significant single findings in the history of planetary science, because it establishes for the first time through direct observation, not through theoretical argument, not through inference from disk models or stellar abundances, but through the actual spectroscopic measurement of an actual object from another star, that the molecular building blocks of planetary systems are distributed through the galaxy in a way that is coherent and broadly consistent from system to system, at least among the kinds of systems that produce and eject icy small bodies of the kind that 2I Borisov represents. The chemistry of planet formation, insofar as Borisov allows us to judge it, is not a local accident. It is something like a universal tendency, expressing itself wherever the conditions for its expression are met, with the same molecules and the same dust and the same icy composition appearing around star after star after star, connected across the interstellar void by the slow currents of ejected material that carry the chemical signature of each system into the galactic commons. The recognition also reveals something about the robustness of cometary material as a carrier of chemical information across interstellar distances and interstellar timescales. For 2I Borisov to have arrived in our solar system carrying detectable quantities of water, ice, and carbon monoxide and carbon-bearing molecules, it must have preserved these materials through billions of years of exposure to the cosmic ray flux of the interstellar medium, through the mechanical stresses of its initial ejection from its home system, through whatever gravitational perturbations it may have experienced during its journey, and ultimately through the thermal processing of its first and, in all probability, only close approach to a star since its formation. The preservation of volatile-rich chemistry through these conditions speaks to the remarkable stability of cometary material under interstellar conditions, to the fact that the cold dark between the stars is, in important ways, a preservative environment rather than a destructive one, protecting the most volatile and chemically interesting components of cometary nuclei against the thermal processing that would degrade them in warmer, more energetically active environment. The universe, it turns out, is good at keeping its chemical archives. The comets drifting through the interstellar medium are not slowly degrading into featureless inert lumps. They are maintaining their chemical complexity across timescales that dwarf the entirety of human civilization by many orders of magnitude, carrying their molecular inventories intact and readable across distances that no other form of matter transfer can bridge. This preservation has implications for the question of how chemical complexity propagates through the galaxy over cosmic timescales, a question that sits at the intersection of astrochemistry, astrobiology, and galactic evolution, and that is becoming increasingly central to the broader project of understanding how the universe has evolved from the simple chemistry of the Big Bang to the extraordinary molecular complexity of the present day. The universe began with hydrogen and helium and trace amounts of lithium, 3 elements, the simplest possible chemistry, a cosmos of gas and gravity and nothing else. Over the subsequent 13.8 billion years, the nuclear furnaces of successive generations of stars have built up the periodic table, adding element after element through the processes of stellar nucleosynthesis and distributing those elements through the interstellar medium via stellar winds and supernova explosions, enriching the gas clouds from which new stars and planets form with progressively greater chemical complexity. Molecules have formed from these atoms in the cold, dense regions of interstellar clouds, growing in complexity from simple diatomics through increasingly elaborate organic structures, with some of the most complex molecules yet detected in interstellar space, including the aromatic molecule benzonitrile and the carbon ring structures known as polycyclic aromatic hydrocarbons, representing chemical species that, on Earth, would be considered moderately complex organic compounds rather than the simple molecules one might naively expect to find drifting in the cold between the stars. Comets participate in this story of galactic chemical evolution by serving as concentrators and carriers, objects that gather chemical complexity from the environment in which they form, concentrate it in their icy nuclei over the timescales of planetary formation, and then distribute it through gravitational ejection and interstellar travel to other regions of the galaxy, where it can potentially be delivered to forming or mature planetary systems. In this role, interstellar comets like 2I, Borisov, are not merely curiosities or convenient probes of the chemistry of other planetary systems. They are active participants in the chemical evolution of the galaxy, agents of molecular transport operating on the largest accessible spatial and temporal scales, connecting the chemical histories of different stellar systems in ways that contribute, however slowly and incrementally, to the progressive enrichment of the galactic chemical environment with the molecular complexity that is, as far as we know, a prerequisite for life. Whether this galactic chemical connectivity has played a significant role in the actual emergence of life anywhere in the universe, whether the delivery of cometary organics to habitable planets has ever tipped the balance from chemistry to biology on a world that would not otherwise have made, that transition is a question that current science cannot answer. But it is a question that the existence and chemistry of 2I, Borisov, makes more concrete and more physically grounded than it was before, transforming it from a purely speculative question about possibilities into a question about processes that we have now directly observed operating in the universe, connecting planetary systems across the interstellar void with a slow but real chemical conversation conducted in the language of ice and dust and organic molecules drifting through the dark. The story of 2I, Borisov, also has a deeply human dimension that sits alongside and intertwines with the scientific narrative. A dimension that concerns the people who found it, who studied it, who wrote the papers, and made the observations, and ran the calculations that built our understanding of what it was. Gennady Borisov, the amateur astronomer who discovered it with a telescope he had built himself, embodies something essential about the culture of astronomical observation, the conviction that the sky belongs to everyone who is willing to look at it carefully and persistently, that extraordinary discoveries are not the exclusive province of large institutions and expensive facilities, that the universe is generous enough with its revelations to reward the patient attention of a single dedicated individual with a home-built instrument in Crimea as readily as it rewards the coordinated effort of a major international observatory. His discovery was not a lucky accident in the pejorative sense. It was the product of years of systematic sky scanning, of the development of real expertise in the recognition of moving objects and unusual celestial phenomena, of the kind of sustained, disciplined attention to the sky that separates the accomplished amateur observer from the casual one. That such attention should be rewarded with the discovery of only the second confirmed interstellar object in human history is a reminder that the universe distributes its extraordinary gifts somewhat democratically, that the criterion for receiving them is not the size of one's institution or the cost of one's equipment, but the quality and persistence of one's attention to the sky. The teams of professional astronomers who followed up Borisov's discovery, who pointed the Hubble Space Telescope and the Very Large Telescope and ALMA and dozens of other facilities at this small, receding visitor from another star, demonstrated a different but equally essential aspect of the scientific enterprise: the capacity for rapid, coordinated, global response to an unexpected discovery, the ability to set aside the normal rhythms of scheduled observing programs and institutional priorities in the face of something that transcends any individual research program's concerns and demands the collective attention of the entire community. This capacity for collective response for scientists in different countries, speaking different languages, working for different institutions, and pursuing different research programs to rapidly align their efforts around a common target of sufficient importance is one of the most admirable features of contemporary astronomy, and it was displayed with particular clarity and effectiveness in the response to 2I, Borisov. The papers that resulted from this collective effort, dozens of them, spanning the full range of observational techniques and theoretical frameworks that modern planetary science commands, represent a genuine collective achievement a scientific portrait of an object from another star, assembled by the combined effort of the global astronomical community, working at the limits of its capabilities, with the urgency that the brevity of the observational window required. And now, in the years since Borisov's departure, the field it helped to establish continues to develop slowly, carefully, in the patient manner of genuine science, building the theoretical frameworks and observational strategies and instrument capabilities that will be needed to make the most of the next interstellar visitor when it arrives. The Rubin Observatory accumulates data. The Comet interceptor waits at its gravitational vantage point. The James Webb Space Telescope peers into the chemical hearts of protoplanetary disks around other stars, building the comparison database against which future interstellar comet measurements will be evaluated. Theorists refine their models of interstellar object production and galactic transport. And somewhere out there in the interstellar dark, perhaps already within the boundaries of the solar system, perhaps still years or decades away, perhaps approaching from the direction of a star we have cataloged and studied, or perhaps from the direction of a star we have barely noticed, the next interstellar object is traveling toward us on a trajectory that the laws of physics determined long before any human being existed to contemplate it, carrying within its frozen interior a chemical message from a planetary system we have never visited, moving through the darkness with the patient, unhurried certainty of something that has all the time in the universe and needs none of it, waiting only for the moment when our instruments will be ready to receive it and our understanding will be prepared enough to hear what it has to say. The universe is speaking. We are learning, slowly and with growing skill, to listen. The sky above us on any given night contains, in all probability, objects we have not yet found, objects from other stars, drifting through our solar system on hyperbolic trajectories, briefly sharing our cosmic neighborhood before continuing their journeys into the dark on the other side of the sun. They are there now, most likely, invisible, not because they are hiding, but because our eyes are not yet sharp enough or numerous enough, or directed at exactly the right part of the sky, at exactly the right moment to catch them in the act of passing. They carry with them the chemistry of worlds we will never see, the molecular signatures of planetary systems that formed and evolved in stellar neighborhoods we will never visit, the frozen record of processes that have been operating throughout the galaxy since long before the sun ignited. They are, in a sense, the universe's way of sharing itself across distances that physical travel cannot bridge, sending out from every planetary system that forms and matures a slow, steady rain of small ambassadors carrying the chemical news of their origins into the galactic commons, where it drifts until it happens, by the patient mathematics of orbital mechanics, to pass close enough to a star with planets and telescopes and curious inhabitants to be found and studied and understood, or at least begun to be understood, in the way that 2I, Borisov, was found and studied and understood imperfectly, incompletely, but genuinely, and with growing depth, the way all real understanding of the universe is built, one careful observation at a time, one patient question at a time, one small increment of knowledge at a time, across the vast and luminous darkness of a cosmos that has been here far longer than we have, and will be here long after we are gone. But that has shown, in the brief window of our attention, a remarkable willingness to reveal itself to those who look.